A stick of length 1 is broken randomly into n parts. What's the probability that any closed polygon can be constructed from those parts? Go ahead and give it a try. First off, you might think about which conditions should be satisfied for being able to construct a polygon. For n equals 3 case, we have the triangle inequality. None of the sides can be longer than the sum of the others. Why is this true? Let's say the largest side has the length L. We need to go from point A to point B using the other two sides, and this is impossible if their sum is less than L. This is regardless of how many sides we have. If the biggest piece is larger than the sum of the others, there's no way we can form a polygon. And notice, when any side length is bigger than a half, the sum of the other side lengths is less than a half, which means the polygon can't be constructed. When all side lengths are less than a half, there's no problem, we can make a polygon. For the sake of simplicity, let's rephrase the question as follows. From n numbers that add up to 1, what's the probability that all of them are less than a half? Let's start with the simplest case, n equals 3. How can we choose 3 random numbers that add up to 1? The truth is, we don't have to. We can simply choose 2 numbers, x and y, and let the third number be 1 minus them. To visualize choosing 2 numbers, we need a 2-dimensional coordinate plane. This square contains all possible ways that 2 numbers between 0 and 1 can be randomly selected. If the sum of x and y is bigger than 1, the third number will be negative. We don't want that, so I will cut this square with the line x plus y equals 1 and get rid of the unwanted piece. The area of the resulting triangle will be our possible outcomes. To find the desired outcome, exclude the areas where x is bigger than a half, where y is bigger than a half, and where the third number is bigger than a half. The remaining area is 1/4 of the previous area. Here we found the answer for the n equals 3 case. I will go through what happens in n equals 4 case before generalizing to higher dimensions. This cube sitting on a 3D space represents the possible ways to select 3 numbers between 0 and 1. I don't want the region where the sum of those 3 numbers is bigger than 1. So I will graph the equation x plus y plus z equals 1, bisect the cube with this plane, and get rid of the region where the sum is bigger. We are left with this little tetrahedron, and its volume is all possible outcomes. To find the desired outcome, I will first exclude the region where x is bigger than a half. This is another tetrahedron, similar to the bigger one, and the similarity ratio is a half, so the ratio of the volumes is 1/8. This is the probability that x is bigger than a half. Notice, all the variables x, y, z and the remaining number have the same probability distribution. That's because they're essentially the copies of the same thing, some variable that will add up to 1. Therefore, their probabilities of being bigger than a half should be the same. We can just multiply the probability of x being bigger than a half by 4 to find the probability of some variable being bigger than a half. Subtract it from 1, and this is the answer for the n equals 4 case. What about if there are n numbers to be selected? Let's focus on the regions we want to exclude. Notice how the structure we're looking at is always n-1 dimensional. The dimension tells us the exponent of the similarity ratio, which is always 1/2, to get the ratio of the n-1 dimensional volumes, let's say mass for simplicity. If the mass representing all possible outcomes is 1, the mass representing one of the unwanted regions is 1/2 to the power of n-1. In other terms, this is the probability that one variable is bigger than a half. Multiplied by the number of variables, subtracted from 1, this is the probability that the parts of the stick can construct a closed polygon. Let's take a moment and go back to where I said all the variables have the same probability distribution. It's not hard to find the probability density function of those variables with respect to n. Once again, I'll start with the simplest case, n equals 3. The probability of x being equal to a given value grows proportional to the distance between that value and 1. So, we know that our probability density function, PDF for short, should look like this. How do we calculate a? We can use the fact that all PDFs have an integral of 1. So I'll set up an integral, do some calculations, and find a is equal to 2. In the n equals 4 case, the probability of x being equal to a given value can be represented by the area of this triangle. So the PDF should be proportional to 1 minus x squared. Remember, the structure we're looking at is always n minus 1 dimensional. When I fix the value of x, there are n minus 2 other variables left to be selected. So some n minus 2 dimensional structure appears, and the mass of that n minus 2 dimensional structure represents the probability of x being equal to a given value. Now we can write a general formula for the PDF. It should be proportional to the distance from 1 raised to the power of its dimension. To find k, set the value of the integral of the PDF to 1. After some calculations, we find k is equal to n minus 1. So this is the general formula for the PDF. On a side note, we can find the mean or the expected value of this PDF and see if it matches with our intuition. This is the formula for the mean of continuous random variables. If I plug in our PDF, the steps for this integral are way too long to show here, but the result will be 1 over n. You can check it on a calculator. And this makes a lot of sense, because if I uniformly randomly select n numbers that add up to 1 and make a guess about what a single one could be, I would probably guess 1 over n, the case when each variable gets equal share. That's all for today. I hope you enjoyed this video. Have a wonderful day.